Bismillahirrahmanirrahim. Today we will be discussing deadlock in operating system. This is one of the very common issues that are observed in our system. What all we will be discussing in this chapter? The discussion agenda of this chapter is in front of you. First, we will try to understand with some examples what actually deadlock is. Then diagrammatically, I will try to represent how deadlock can be represented in order to enhance your further understanding. Then we will be discussing what are the characteristics of deadlock. Next, we will be talking on different methods to handle deadlock. That includes deadlock prevention, avoidance, and detection. At the end, we will talk on mechanism, how we can get our system back if it ever face deadlock.
The first point that we are going to discuss now is to understand what is deadlock and how it is a problem. Deadlock basically is a problem or a point where our system gets stuck and you feel that things are not moving ahead or the processes are not getting executed. You feel your system gets hanged. So this is the situation when your system goes in deadlock. So we'll be now discussing this problem in detail and would try to understand pictorially how we can define and understand deadlock, and similarly how it can be represented when it appears in your system.
What is a deadlock? The definition of deadlock says set of blocked processes, each holding a resource and waiting to acquire a resource held by another process in the set. What does this definition mean? Let's develop our understanding with the help of an example. For example, we have two tape drives in our system and there are two processes P1 and P2. Both of them are holding one tape drive each, but requires other one in order to complete their respective task. Blocked state, as mentioned in definition, is the waiting state when a process is waiting on some resource to be assigned to it or it is being executed on some resource. We have discussed block state in chapter 2. So now the situation is two instances of tape drives are there and both of them are being held by two processes each. But they are not proceeding ahead as they require one more instance of tape drive. So what they are doing? Neither they are moving ahead themselves nor they want each other to move ahead. So this situation is known as deadlock. Deadlock is a very common problem which we may face in our daily routine. Here a road and bridge is depicted in the diagram to make you understand more what deadlock is. Traffic is shown in the diagram. The cars represent processes and the road and bridge in between two roads represent the resource. These resources are being used by the cars to reach to their respective destinations. Now, as you can see, both the roads are two-way, but the bridge in center is one-way. Traffic on both sides of the road have already acquired their sides of road, but want the bridge to be given to them too. Now, since only one side of traffic can cross the bridge at a time, so both sides of traffic confront each other when they reach the bridge. The traffic goes jam unless and until one side of traffic backtracks. The jam cannot be finished. So this situation is known as deadlock, as no one gets its work completed using all required resources. Now, if one side of traffic is backed up, the starvation may be the result for the traffic on that side. How? It may be possible that only one side of the traffic is always backed up when there is deadlock, so the cars on that side may not get enough time to use the bridge. Similarly, if one process in your system is always deprived of resources, it may face starvation.
After developing an understanding with the deadlock problem, now we are going to represent a system model and see how deadlock appears in our systems. So here we'll be using different graphs, diagrams to represent deadlocks when it appears in our system and how it stucks the overall system. Your system performance goes to 0, and if you remember in chapter 3 it was a criteria that CPU utilization should be maximum. But when deadlock occurs, your system performance or the CPU utilization goes to almost 0 or becomes minimum. So this is the violation of the criteria or the optimization criteria that we had set in previous chapters. That is the reason deadlock is known as a problem, not only for the system but also for the user of the system. So now let's proceed with some diagrams or models in order to see how deadlock can be represented diagrammatically if it appears or happens in our system.
So, how deadlock can be represented in our system diagrammatically? We will try to create a system model showing deadlock. The resources in our system can be represented with alphabet R. Resource, as you all know, can be hardware such as CPU cycles, memory, I/O, etc. One resource may have different instances, such as we have different types of memory in our system, like primary memory, secondary memory, and different hardware represent them, such as for primary memory we have RAM and ROM, and for secondary memory we have different tapes, different types of disks such as hard disks, flash drives, etc. So the instance of a resource R can be represented by alphabet W. Processes can be represented with alphabet P. How a process utilizes a resource? The sequence is: process first has to request the resource. If the resource is available, it will be assigned to it. The process will use it, and after using, the resource will be released so that other processes can then use it.
Now, what are the factors that recognize that your system is in deadlock? So there are some factors or characteristics of deadlock. If those characteristics start appearing in your system, that means your system is going to lock in some problem which is known as a deadlock. So some characteristics for identification if the system is in deadlock or not. Let's see what are those characteristics.
There are some characteristics or conditions or requirements for a deadlock. These conditions are mutual exclusions, hold and wait, no preemption, and circular wait. Let's discuss all of them one by one. Mutual exclusion has already been discussed in detail in previous chapter. Mutual exclusion means one process at a time will be using the resource. Second condition is hold and wait. This simply means that a process will be holding a resource and waiting for another resource to be assigned to it, and that resource may not be available at that time. So this is the exact explanation of deadlock. The process will not proceed its execution with one resource. Instead, it will be waiting for the other resource. Third condition is no preemption. Preemption, as you all know, is to take away a resource from a process without its consent. We have seen this in chapter 3 when we were discussing different CPU scheduling algorithms. Some of them were preemptive and some were non-preemptive. So here, no preemption means a resource cannot be taken away from a process forcefully. The process can only voluntarily release the resource after its use. Fourth requirement or condition is circular wait. Processes are waiting for each other in a circle. They actually are not waiting for each other, rather they are waiting for the resource held by other processes. Such as in diagram, P node is waiting for a resource held by P1 and P1 is waiting for a resource held by P node. So they are forming a circle. Similarly, big circles can be made when more processes will be involved in the circular wait, such as P node will be waiting for a resource held by P1, P1 will be waiting for a resource held by P2, P2 will be waiting for a resource held by P3 and so on, until last process in circle such as Pn will be waiting for the resource held by P node. It is important to mention here that in order for deadlock to occur, it is important that all these four conditions must occur simultaneously. If one condition does not occur, and other three are present, still deadlock will not happen. Now we are going to create resource allocation graph. Resource allocation graph will represent the pattern how resources are allocated to different processes. So, as we have already mentioned earlier, resources will be represented with alphabet R and processes with alphabet P. So we now need to connect them with some edges. Two types of edges are mentioned here, request edge and assignment edge. There is one more type of edge which we will discuss later on. So request edge will be drawn from a process towards resource, showing that a process is requested a resource. And if the requested resource is assigned to the process, so the edge will point from resource towards process. Both the edges must be directed so that you can differentiate which one is request edge and which one is assignment edge.
Now we are going to draw a system model. System model is actually a representation of the system when your system gets stuck in deadlock. So what are the components that will be used to draw deadlock situation? System model is a collection of different entities for the representation of deadlock. So different components are mentioned here that we will be using in the drawing of deadlock situations in the coming slides. The basic components that I want to explain are these 4 different types of components which will be required when we are going to draw a resource allocation graph. Generally, a process is drawn with circle. Here you can see a process is drawn with circle, and if you are not going to draw circle, you can represent process with P. If there are more than one process, you can number the processes P1, P2, P3, P4, and so on. You can also write these a number inside this. Let me write it here. Inside this circle, P1, one process, circle, P2, another process. So circle represent the processes. If there are more than one processes, you can circle and write the process numbers in that particular circle. The next type or next component is the resource. How we can draw a resource? So resource is drawn with square. Resource is drawn with a square, or you can also use a rectangle. Simply a square or a rectangle. So if there is a single instance of a resource, that means a single type of that particular resource is there. For example, you generally have one keyboard, so a single square is enough. But some resources have more than one instances. For example, memory is a resource. If you are having single type of memory, a single square is enough to draw. But as you can see, you have more than one type of memories in your system. For example, you have primary memory, you have secondary memory, and then in primary memory you have different types of memory, RAM, ROM, and in secondary memory you have variety of memory. That includes your hard disk, that includes your floppy drives, and so many others. That means memory is one resource, but it has multiple instances: primary memory, secondary memory, and so on. So in that case, you need to draw as many instances as a resource is. So that particular number of resources are drawn inside this big square, like this. Small squares are drawn inside this big square. For example, if a resource has 2 instances, so 2 squares are drawn inside a big square. If a resource has 4 instances, so 4 small squares are drawn inside the big square. But if there is a single resource, only one square is drawn like this. Now, how we can draw request edge? Edge is drawn, as we have said, with a directed arrow. So if a process P is requesting for resource R, how we can draw it? Here you can see the arrow must be drawn from the process towards the resource. Arrow is directing towards the resource. Here in this case, you can see PI is requesting for resource RJ. Now RJ, as you can see, has 4 instances. PI wants any one of 4, not all 4, any one of 4. It can request all of the 4, but here in this case, the requesting edge, as you can see, is pointing or targeting toward on the boundary wall of this resource, the bigger square. Here you can see. If it wants to have a particular instance of the resource, so you can draw the arrow right towards the border of that particular instance. For example, it wants this resource but that particular instance of the resource. So you can draw the arrow from the process towards that, right at the border of that small instance, that small square. But since in this case the process is requesting resource RJ, so any of the 4 instances can be assigned to it. Now how we can draw the assignment edge? How you can draw the assignment edge. Since Pi was requesting any of the 4 resources, now anyone available is assigned to it. Keep in mind, if you draw the arrow right from the border of the big square towards the process, that means all of the 4 instances have been assigned to this process. So if you are going to assign a single process, you need to draw, as in this case I have drawn it from one particular instance. You need to draw it from a single instance. That means only one instance of this resource has been assigned to P1, while the 3 other resource instances are still available to be assigned to other requesting processes. So 3 are still available while 1 has been assigned. But if you have drawn it right from the border of the big square, that means you have assigned all the 4 instances to a single process. So no other process will then have to acquire this resource. Other process will then have to wait. So keep in mind while drawing the resource allocation graph, if you are going to assign single instance, you have to draw it right from that particular small square. If process is requesting for particular instance of the resource, so you have to draw the arrow from the process to that particular instance. If it is requesting for any of the instance, so you can draw it right at the border of the big square. But specific instances, if required, you can drag the arrow to the edge of that small square. But when assignment is done, similar method should be followed. Not all the 4, not all the 3, not all the 2 instances are assigned to a single process. Only a 1 instance is assigned. So you have to draw the arrow from the resource, that particular instance of the resource, from that particular instance of the resource towards the process. If you have drawn it right from the border of the big square towards process, that means all of the instances have been assigned to a single process. Keep in mind and do not make this mistake while drawing resource allocation graphs.
This is a diagram showing resource allocation graph. As you can see, there are 3 processes, P1, P2 and P3, and 4 resources, R1, R2, R3 and R4. Some of the resources have more than one instances, which are shown by small circles inside the big square. So P1 is requesting resource R1, but R1 is assigned to process P2. P2 is holding R1 and requesting for resource R3, but R3 is assigned to P3. Resource R2 has 2 instances which are assigned to P1 and P2 each. Resource R4 has 3 instances and is not requested by any process. So all 3 instances of R4 are available. So this is how we draw resource allocation graph. This is resource allocation graph showing a deadlock. Can anyone highlight the deadlock? The best example to highlight deadlock is to monitor the circular weight. Now check how many circles can be drawn among processes. We can see 2 circles here. How? One circle, P1 is waiting for P2 and P2 is waiting for P3. P3 is then waiting for P1. This forms one circle. Another, P1 is waiting for P2, P2 is waiting for P3 and P3 is waiting for P2. This forms another circle. All of the 3 processes are in deadlock as all of them are holding some resources and waiting in circle for another resources held by other processes. Mutual exclusion is also applied as one resource can be used by single process at a time, and no resource can be forcefully removed from a process. Since all four conditions of deadlock can be observed in this diagram, so this represents a deadlock. We need to apply some mechanism to eliminate deadlock, which we will be discussing later on. This is another graph which has a circle, but still it is not considered as deadlock. Why so? Because we have deadlock breaker in this diagram, which are process P2 and P4. As you can see, a circle between P1 and P3 on resources R1 and R2. Both resources have two instances. One instance of R1 is with process P2 and another is with process P3. Similarly, one instance of resource R2 is with process P1 and other is with P4. Since P2 and P4 have no further request, so they can break the circle between P1 and P3. After utilizing, P2 will release resource R1, which will be assigned to process P1, and the circle will break. Similarly, P4 will utilize resource R2 and release, which will be then assigned to process P3, and hence the circle will break. So whenever there are circle breakers in the resource allocation graph, this situation is known as live lock. Live lock is flexible and temporary as compared to deadlock, which is hard to break and generally long lasting.
That is all for now. In today's discussion, we started a new chapter, deadlocks. Things that we had discussed in today's discussion related to deadlock are that we first tried to develop an understanding with the term deadlock. Deadlock actually is a problem in which you see your system gets stuck and things are not getting done or properly done. So what is a deadlock? How we defined deadlock in today's discussion? This is a situation mainly in which two or more than two processes, each holding some resource and trying to avail other resource that is held by the other processes. So in that situation, processes are holding some of the resources but are not utilizing those resources and waiting for those other resources which are held by some other processes. So every process actually waiting for the other process to release its resources. They are not completing their task, rather focusing on other processes. So this is a sort of a lock between processes. They are waiting for one another to release some resource, and no process is willing to release a resource. This issue, deadlock problem, is commonly arised in competing processes. Generally, the cooperating processes try to negotiate with one another and release the resource for the one who requires the resource on priority basis, or the process whose priority is high. But with the competing processes, deadlock problem generally arise. Then we discussed different factors due to which deadlock occurs. 4 common factors or 4 common characteristics of deadlocks have been discussed. That is, no inclusion, no preemption, mutual exclusion. Third is hold and wait, which is actually the definition of deadlock. And the fourth one is wait in a circle, a circular wait. So if these four characteristics or these four factors appear simultaneously at the same time, only then system will stuck in deadlock. If any one, any two, or any three of the factors are appearing in your system, still your system is safe from the deadlock. But if four factors, four characteristics, all of these four are appearing or happening simultaneously, then your system is going to stuck in deadlock. We then represented a system model, how we define or how we draw a model showing if our system is stuck in deadlock. We'll continue this discussion in coming lectures and we'll draw some diagrams showing how deadlock can occur in our system using the system model we have already defined in today's discussion. We will be also discussing the methods by which we can handle this problem, deadlock problem. So this is the introductory discussion on deadlock chapter. Further more discussions will continue on this chapter in the coming lectures. If you have any queries, you can ask me on KCMS or email me. I thank you all.